today we'll be going through a largest color value in a director graph, right? The question is as follows. So you're given a director graph, so the edges go from A to B and it's not undirected, and each edge has been colored with one color, right? And these colors can vary up to 10 to the power of 5. And the idea of this question is to identify the highest frequency at which a color occurs in any path on a graph. So what I mean by this, right? So let's take a look at example 1, right? So we have 5 nodes in this graph, and notice that 0 to 4 are red, 3 is blue, and 1 is purple. Notice that a simple path is from a starting point all the way till like a ending point, for example, right? It could be even shorter, but it doesn't really matter because you're going to maximize it anyway. We have two simple paths here, right? 0 to 1 and 0 to 3 4. And notice that in this path, the frequency of the colors in it is 3 for red, 1 for blue. In this path, the frequency for red is 1 and the frequency for purple is 1. The answer to this question is going to be 3, because 3 is the frequency of the color red, which occurs 3 times in this path, right? And there is no other path with a color of any higher frequency, right? And obviously in this question you would understand that if you were to have a cycle, it's kind of invalid, because let's say there has to be a cycle, right? Then there will be just a path of infinite length that would satisfy the criteria. For example, let's say there was like a node 5, so it'll be 2 3 4 5, and then you go back to 2. You notice that there'll be a cycle here. And you can always just go through cycle again and again and again. So in that case, the frequency of the highest color would be pretty much infinite, which is why it's not really a valid scenario, and return -1, right? So if you look at it from that point of view, the problem becomes gets split into two things. One thing would be to identify whether there's a cycle in a graph, and if there is a cycle, you return -1. Otherwise, you identify the longest path from start to finish, and then which contains you identify the highest frequency of any color, right? So let's get right into how we start coding it. So first I create an adjacency list, and I keep track of all the edges in the graph, right? So for example, we have adjacency list of elements, and then essentially adjacent list edge 0 dot append edge 1, so 0 arrow towards edge 1. Notice that that's a simple case in which we know that there's already a cycle, which is a case where edge 0 equals to edge 1. It means that it points to itself, so there's an infinite cycle here as well, right? And I also keep an array called the in degree. So the in degree of a node in a graph is the number of arrows that are pointing to it. So for example, 0 has an in degree of 0, 2 has an in degree of 1, 1, 1, 1. If there was a node 5 and pointed to 4, then 4 would have an in degree of 2, right? So now why do we calculate the in degree? The in degree will help us identify the starting points of potential paths, right? Since there are no cycles in a valid scenario, we need to figure out the maximum frequency. We need to know that where can we start this path from, and we can start it when the in degree of the node is 0, which means there's nothing coming into it, so this is the clearest start. So that will help us to begin our DFS and start things going, right? So I'll first go through how I detect cycles in this graph. I use a technique called the topological sorting, right? So topological sorting pretty much ensures this one important feature, which is that okay, let me just write down the topological sorting of this graph, right? So I have 0, 2, 3, 4, 1. This is one valid topological sorting, but there can be another which is just 0, 1, 2, 3, 4. And the idea is that if you look at this array, right, if you drew arrows, which are the edges, all the arrows will point rightwards, like 0 points to 2, 2 points to 3, 3 to 4, and 0 points to 1. There will be no arrows pointing backwards if there are no cycles in the topological sort. So if we detect any arrows going backward, we will immediately know that there's a cycle in this graph and return -1, which is what we do in this step, right? First of all, we perform the topological sort by using a DFS. The idea is to pretty much go through all the neighbors, do DFS on them first, and then only at the end of it do you append the first node. So at the end of the day, you need to reverse this topological array to get the actual topological sorting, which you can see here, right? So and once you get that, there are several conditions where we immediately know that there are there isn't a valid topological sort and there could be cycles. One is the case where the topological sort is empty, right? In case we return -1, right? Which means by right the length of the topological sort should be the same as the length of the number of nodes. Actually, this one is not relevant here. We can just take it out because the step below it performs the step anyway, right? So return -1 in that case. And this is how we check through this array. We use a scene set. So for example, we are at element 3, right? We check if which element 3 points to, and if it points to any of the elements already seen before, like 0 and 2, then we know there's already going to be a cycle. In that case, we return -1, and then we call it a day on that, right? So that's how we detect cycles using topological sort, right? And to solve this problem, we'll be using some elements of dynamic programming here, and I'll just go through what the DP array as a 2D array would signify, right? So the DP array is two-dimensional, having node and color, and the value at each cell in that DP matrix is going to be the longest chain of this color possible, starting at the node that is specified, right? So what does this mean? So this means that DP0 red would mean that what is the maximum number of red elements that start when I look at node 0. So in this case it's going to be 3, and in a similar way, DP2 red is also going to be 2 also. And also notice this, right? So let's say if I have DP2 and then I have blue, notice that this is going to be 1, even though this color is not blue. Notice that from this point to the end of the path, there is 1 blue in it, which is why there is going to be a 1, right? So we can form some recurrence relations using this formula. So I look at the key thing to understand before you do that is that the parents, the counts depend on its children's counts. So if I know the counts of the different colors starting from 2, I can know what the counts are going to be for node 0. Right? What do I mean by this? Right? So let's say if I look at, so let's look at this recurrence relation, right? For example, dp0 red, right? So how many red colored balls start from node 0? So it's going to be the maximum between itself and in this case it only has one children, but there could be cases of many other children, right? Because there could be one here or whatever, right? dp2 red also plus 1. You need to add the plus 1 there because 0 is also red, right? But let's say if it was some other color like blue or purple, then you're not going to add anything to it because this does not contribute to blue or purple. So yeah, so that's pretty much the recurrence relation as you can see in these conditions. Right, so let me just go through the DFS and how we populate this DP matrix. So yeah, so as normal, we have visited array and we iterate through every neighbor in the adjacent list, right? And notice that we recursively call the DFS function again first before we perform or before we derive these numbers. The reason for this is because we need the children's DP values to be populated before we can derive the current value. This makes sense, right? Because you will need the values of the numbers here, numbers here, numbers here before you know the values here, which is why this is after the step. And yeah, we iterate through all the colors, and this is a recurrence relation I mentioned on the top. If for that color it's the same of the color of the node, then you add 1, otherwise it's just going to be the neighbors count, right? Neighbors count plus 1 or neighbors count. Yeah, and we keep a variable called self.mxv, which is going to be the maximum frequency, and then this just pretty much helps us update and identify the final value in the end. So yeah, so that's pretty much how you solve this question. Yeah, you return self.mxv, and yeah, the solution is pretty efficient. So yeah, thanks for watching. I hope to make more soon. Bye bye.